So on page 4 of the notes, it says there are 2 methods to solve. We're actually going to use a third method because that's the one that I prefer. The third method is going to be using the LCD as dynamite to destroy all the denominators. So instead of using a nice little friendly creative form of 1 where we're just preserving the value of the original fraction, we are going to be using our LCD to destroy all of the fractions. So on these problems, just like on the adding and subtracting, we are going to be stating the LCD first. We're just going to be using it in a different way. First method and second method, you can use cross products if you want. Some students like to add these 2 fractions together first and then multiply through by the denominator. But I personally think using the LCD as dynamite is the easiest way. So folks, we're going to start our first problem by identifying our operations and anything else we have going on. We've got addition and we've got an equal sign. Now, I like to think of the equal sign as being just a stick of dynamite that we will use to explode our fractions. Such artistry. So dynamite, we're going to light it, we're going to blow up the fractions. Now, on the problem that I did on the board, we just needed to multiply through by 5 to get rid of that one denominator. Here, I have 3 different denominators to get rid of. But if I multiply through by the LCD, I'm going to be able to destroy all of them at the same time. So using our strategies from earlier, if I factor this one, well, x plus 3 is just x plus 3. It's its own factor. Now the 6, since it's a monomial, we're going to break that down into 2 and 3. And the 18 we're going to break down into 2 and 9. And the 9 breaks down further into 3 and 3. So trying to figure out what our LCD is for all of these fractions, the greatest amount of x plus 3's we have in one fraction is 1. So that's going to be part of our LCD since that will blow up our first fraction. Now, what's the greatest amount of 2's that we have in one fraction? 1. So 1, 2 will be part of our LCD. What's the greatest amount of 3's that we have in one fraction? Those 2 3's. So 3 times 3 times 2 will give me 18. And that is what we are going to use as our dynamite to blow up all of our fractions. Now, as I said on the board, we have to keep the equation in balance. So I got to multiply this by the dynamite, and I have to multiply this by the dynamite. And actually, we're going to have to distribute it to the entire side. So every single fraction here is going to get multiplied by the dynamite. So it's kind of a lot of work to show in the notes. As we do the first 4, you're probably going to be able to figure out how to show less work on these, but I would like you to show it this way just so you can see what is happening in these problems. So we start off by laying down a stick of dynamite. 18, x plus 3. And you can put it over 1 just to make it look more fraction-y. So I'm going to multiply that by my first fraction. 4 over x plus 3. Sometimes I like to box these off because they all turn into their own little simplifying problem. Plus, now we're going to lay down the dynamite in front of our next fraction. So 18 times x plus 3 again over 1 times the second fraction. Then our equal sign, one more stick of dynamite down, 18 x plus 3. So everything in purple was our original equation. Everything in red is the dynamite or the LCD that we are going to be using all of those denominators. So each of these boxes is kind of its own little mini problem of the very first thing we did in this chapter with multiplying. So as I look in my first box, what's going to cross off? The x plus 3's. Goodbye, denominator. No more fraction. What I am left with is 8 times, 18 times 4. So 18 times 4 is 72. So wow, that ugly first box just straight up turns into 72. Lovely. Then we move to simplify in the second box. Is there anything that I can cross off? Should be able to cross off that denominator. What am I going to be able to cross off the 6 with? The 18, so a 6 out of there, a 6 out of there, and we're left with a 3 times x plus 3 times 5. I'm going to put the 3 and the 5, those monomials together in front of the x plus 3. Oop, and then equals, it's chunky whiteout time, equals our last box. What's going to cross off in our last box? The 18s. Goodbye. Goodbye. So I'm left with 23 times x plus 3. So making sure that in between the stuff that's left over, you are putting multiplication since there's a dot there, multiplication since there is a dot there. So folks, take a look at the magic that just happened. Do we have any more fractions? No. And suddenly this has turned into, although there are big numbers, a fairly simple Algebra 1 equation. So let's go ahead and what is your gut telling you we should do next? Distribute. Pew, pew, and pew, pew. I'm going to save us a little bit of time here and let you know that 15x plus 45, 23 times x is 23, and 23 times 3 is 69. Nice. What would I do next to this problem? We're going to combine our like terms. And we get 117 plus 15x equals 23x plus 69. So what do we do now? Going back to Algebra 1. We're trying to figure out what x is equal to. We're trying to solve for x. Yes? Get x on one side. Isolate the variable. So we could subtract 23x to move him over, or we could subtract 15x. What do you guys want to do? Subtract 15x. Let's keep stuff positive. I love it. So minus 15x. And that gives me 23x minus 15 is x. And let's go ahead and get this out of the way. Subtract 69 over to the other side, and 117 minus 69 is 48. How do we get that x all by itself now? Divide by 8. And x is 6. Don't put a box around it. This is something new that we haven't had to talk about yet because we've never encountered this in any other type of equation solving that we do. These rational equations have something called restrictions. And that's actually going to be our first step in the problem from here on out, is stating any restrictions that we have on x. You can think of a restriction kind of as a rule like, hey, don't walk on the grass. Hey, don't run with scissors. Hey, don't do this. Why? Because it's a bad idea, because it leads to not good things. So if I am looking at this original equation, I can divide by 18. I can divide by 6. What happens if I plug negative 3 in for x? What's negative 3 plus 3? 0. What's 4 divided by 0? We better turn to our calculators. 4 divided by 0 is error. You cannot divide by 0. Remember, folks, I can take the $0 I have and divide it amongst all 26 of you. 26 of you. And how much would you each get? $0. So 0 divided by 26 is 0. But I can't take $26 and divide it into 0 parts. So if I have a pie and I'm trying to cut it into 0 pieces, even the whole pie is still 1 piece. So explosion, we can't do it mathematically. You cannot divide by 0. So state restrictions first. You can't divide by 0. So I look at 18, that's okay to divide by. I look at all of the denominators and I try to figure out what values of x are not going to be allowed. So I looked at each denominator, found the one with the variable, and it's kind of like the opposite of finding an x-intercept. We say, okay, what value of x would make this equal to 0? Because we don't want that. So x, we do not want to be equal to -3. This is our restriction. So x can't be equal to -3. Why? Because it makes the equation false. It's not true. We get undefined plus 5, 6 equals 23/18. That is not good. So once we get our final answer, we are always going to have to check it against our restriction. So we got x equals 6. Is that all good as far as our denominators are concerned? Yep. 6 plus 3 is 9. I can divide by 9, so it's all good to go. Folks, the restrictions are going to have an impact on the next part of this chapter where we start graphing and looking at asymptotes. So we're going to get some good practice with this as we start solving. So LCD, find it, blow up all those denominators, find your solution by using Algebra 1 strategies usually, and compare that against your restrictions. So let's go ahead and look at the problem directly below it. First, we identify our operations. We've got adding and we've got an equal sign. Now that equal sign means that we can use our LCD as dynamite and blow up all of the fractions. So first, what is our LCD? What are we going to use as dynamite here? I've got x plus 3. That is its own binomial factor, so x plus 3 will be part of our LCD. 2, can't factor tree that. 10, we can break down into 2 and 5. So the greatest amount of 2's that we have in one fraction is 1, 2. Greatest amount of 5's we have in one fraction is 1, 5. So what are we going to use? 10. 2 times 5. So 2. 5. Dynamite. And I'm going to multiply each of my fractions by this to destroy all of them. So I'm going to lay down the dynamite first. 10, x plus 3. You can put it over 1 if you like. Times the first fraction. 2 over x plus 3. Then we've got our addition sign. And we're going to multiply our second fraction by the dynamite. So 10, x plus 3. 1 times the second fraction. 3 over 2. Equals dynamite in front of the last fraction. Before we go any further, do we have any restricted values for x? What is the one thing that x can't be? -3. So x cannot be -3. We'll go ahead and state our restriction right next to the LCD. So any other value is fine. It's only -3 that would make this fraction dividing by 0. So now the fun part, all the blowing up of the denominators. So we get to cross off x plus 3 with x plus 3, and we're left with 10 times 2, or 20. In the next box, We know we should be getting rid of that 2. What are we going to cancel it out with?
10.
The 10. So that will leave me with a 5, the x plus 3, and the 3. So we're going to smush our monomials together. 5 times 3 is 15. And then x plus 3 equals 10. We'll cancel out the 10 in the last fraction. And we're left with 19 times x plus 3. So now we have this nice, much easier ground level equation. So let's go ahead and see what happens when we simplify by distributing.
Oh, you're looking at
20 plus 15x plus 45 equals 19x plus 57. Let's combine our like terms first that are on the same side of the equation. So I've got 20 and 45 over here. Do I need to subtract the 20 to move it to be with the 45? Nope, they are on the same side. So we can just straight up add them together. So 65 plus 15x equals 19x plus 57. Now, it's totally up to you which side you want to isolate x on. You will get the same answer, but I like to try to keep x positive. So if we subtract 15x, that would give us 4x. And then if we subtract 57, that gives us 8. Divide by 4. Divide by 4. And x equals 2. We don't put a box around it though because we have to check it against our restricted values. Am I allowed to have 2 in the denominator? Yes. The only x value out of the infinite amount of things that are possible is -3. So because my answer is not that, that's our solution. Easier than what we've been doing? I think so. Nice breath of fresh air after complex fractions. All right, folks, so let's go ahead and take a look at our next problem. This one is a little bit messier, and the first messy thing that happens is our operation that we have going on. What do you think we should do with that subtraction symbol? We're going to float it up to the top of this fraction and distribute it to all 3 of those terms. So I'm going to make this a plus and shift it up to that numerator, making this negative, this positive, and that positive as well. It changes the signs of the entire top. So now let's figure out what our restrictions are. What can't x be equal to? Looking at that first denominator, -5 is one of them. What else can it be equal to? -3. Looking at that middle fraction, it's like trying to guess what x value would make that 0. We're going to factor it. So you actually might want to find your LCD first and then state your restrictions. So let's go ahead and factor this. Product of 15, sum of 8, that's going to be x plus 5 and x plus 3. Product of positive 15, sum of positive 8. And as we can see, those factors have the exact same restrictions. -5 would make that 0, and -3 would make that 0. So those are my restrictions. What is our LCD dynamite going to be for this one? Greatest amount of x plus 5s we have in one fraction, 1, x plus 5. Greatest amount of x plus 3s we have in one fraction, 1, x plus 3. Would you like to show a little less work?
Yes.
You can continue to show it this way if you want, laying down the dynamite in each of those fractions. But here is another way that you can show a little bit less work. If I multiply this first fraction by the LCD, what is my denominator going to wipe out? X plus 5 is gone, and the x plus 5 in the LCD is gone, leaving me with 2x times x plus 3. If you did not like that, please continue to show the work of putting it out in front. Then, for my second fraction, when I multiply this by the LCD, the x plus 5 and the x plus 5 cancel, the x plus 3 and the x plus 3 cancel, and what I am left with is simply the top of that fraction. So negative x squared plus x plus 10. Then we bring down the equal sign. When I multiply that last fraction by the LCD, the x plus 3 and the x plus 3 will cancel, leaving us with 3 times x plus 5. Personally, I still like to show this boxed out, everything written method, just because I found I'm a lot less likely to make mistakes that way. So if you start doing it this way and you find that you're like missing stuff to multiply, I would go back to showing all of the work. It's better to take a little longer and be correct, and then take a little less time and be wrong. So folks, I'm going to turn you loose on this next part. Get as far as you can in 1 minute. 2x times x, 2x squared. Something that I noticed on some of the homework quizzes was when we were handling this distribution stuff, sometimes students were just putting 6 and forgetting to put the x with it. So just be careful. You're multiplying the coefficients and tacking the variables onto the end as well. So then negative x squared plus x plus 10 equals, distribute, 3x plus 15. So then if I have 2x squared minus x squared, we have x squared, or just 1x squared. 6x plus x is 7x. And we got the 10. Equals 3x plus 15. Why is this problem a little bit different than the ones we've been working on? It's got an x squared. Folks, how do we handle a quadratic equation? Factoring. So square root would work if we only had x squared and didn't have the 7x and 3x. Quadratic formula is an unfortunate last resort that we should use if we can't factor it, but I'm like 90% sure that everything in this chapter should be factorable. Yes?
What if you just minus the 7x and then minus the 15?
and then square root. But the whole thing is we have to get those x's together, because if you square root, you're going to have x is equal to the square root of x. It's like when you're trying to define a word, like what's a cat? It's like, oh, a cat is a, adult kitten. It's another cat. So it's kind of redundant and cyclical because you're saying x is equal to something in terms of x. So we have to somehow break this down into two single x's. So we are going to have to try to factor it. So try to factor. Try to factor right now?
Yes.
Yeah.
No.
Like this?
No.
No. Why not?
Because.
What should we do with the whole 3x and 15?
Get them to the other side.
Move them to the other side. So try to factor, and remember, it needs to be equal to 0 before you factor. So subtract the 3x, subtract the 15. So x, scratch that, x squared plus 4x minus 5 equals 0. Can we factor that?
Yes.
Product of negative 5, sum of 4. What are my two numbers? Negative 1 and positive 5. Wonderful. So now, if something times something equals 0, then either this guy equals 0 or this one equals 0. So folks, that's what factoring does for me, is it takes this x squared and this x, which I can't isolate, and it breaks it down into a single x and another single x that we can isolate using the zero product property. Neat stuff. So then x is equal to 1 and x is equal to negative 5. Folks, what is the problem with these two answers? So negative 5 is not good when we look at our restrictions. So negative 5 makes this fraction undefined, which essentially invalidates the whole equation.
What about the 1 though?
So the 1 is all good.
Oh, yeah.
So folks, here's the deal with these. Sometimes you'll have two solutions. Sometimes you'll have one solution. Sometimes you won't have any solution at all. It all depends on what the structure of the equation is. Do we get a quadratic somewhere in here? Do we get an algebra 1 equation? And what are our restrictions that make it likely or unlikely? So sometimes both solutions will work. Sometimes neither of them will work. So that's why it's really important that we check. So folks, we call this situation of this not working an extraneous solution.
Do you have to write that out every time?
Nope, just here. Extraneous solution. We will be encountering extraneous solutions in every unit for the rest of the term. So we're going to get very comfortable with this term. What that word extraneous means, it's a form of extra and erroneous. You guys know what erroneous means? It means wrong. So you can tell someone they're being erroneous if they are wrong. So extraneous is a mixture of extra and erroneous or wrong. So it's a solution that we find, but it doesn't actually work. So folks, if you're sifting through going like, oh, well, wait, like, why doesn't it work? We didn't do anything wrong algebraically. It's just something that can happen when you multiply through by the denominators and destroy them. A lot of times you are mathematically removing the thing that causes the restriction. So by multiplying through by the denominator, it's all fine. It's totally legal to do, but sometimes it mathematically removes the restriction. So that's why we're always going to have to check our answers. So in previous chapters, it's like, yeah, check your answers to make sure that you're not wrong. It's a good thing. Now we have to check our answers to make sure that the equation isn't going to consider them wrong. So we always have to check them against our restrictions. So extraneous solution is what this is called. I would still want to see this in your work, like, hey, I found it, cross it off to show, yeah, it did not work when we plugged it back in. Yeah?
Question.
Yes?
How do you do the, like from the very beginning again? Like when the, without showing the boxes? you know.
Oh, how did we bypass that work?
Yeah.
So we still have to multiply each of these fractions by the LCD. So if I multiply the LCD by this first fraction, this denominator is going to cross off that part of the LCD so that I'm left with the 2x
Oh.
and the x plus 3.
Okay, so it's just gonna be the top number times the LCD.
Yep, so then it's just 2x times x plus 3.
Alright. Thank you.
So that, I just wanted to show you how to do the shortcut. I'm probably actually not going to do that on the next problem. Ooh, and I like this next problem because this encounters something that we've had some trouble with. So first, identifying our operations. We've got an equal sign. We can use it as dynamite. So that minus sign, what do you want to do with that?
Make it
Plus and float it with the top. So now for the LCD. X plus 1, I cannot factor that any further. X minus 1, I cannot factor that any further. What about x squared minus 1? Difference of squares. So x plus 1 and x minus 1. So what's our LCD? X plus 1, x minus 1. Wonderful.
Not me.
So that's our LCD. Then what about the restrictions? What can't x be?
1 and negative
1 and negative 1. Miss Cara, does that matter what order we write those in? Nope. But I do want to see those two things as part of your work on the homework. Stating the LCD, I'm going to have you do that on the test as well, and stating the restricted values. So using whichever method you like, either the box method or the covering up method, I want you to try to do the first step of this problem, destroying all of the denominators by blowing up those denominators using the LCD.
So it's just an extraneous solution. What if like all the answers are?
Then your final answer is no solution. Folks, how do we do with this first setup?
Very nice.
One thing to be careful of in the next step, and this actually came up in pre-calc today too. When I distribute this -1, I have to distribute it to both of those, as in the sign goes with it. So that negative travels with that 1.
Alright, speed on that.
All right, so 2x minus x is just x. -2 minus 1 is -3 equals -2. We add the 3. And x equals 1. And are there any issues with that? Yeah, so it makes one of the fractions, not the first one. I can divide by 2 just fine, but 1 minus 1, that is 0, and I cannot divide by 0. So we got a problem with this restriction. So we found a solution. It's an extraneous solution. So our final answer to this problem is not just this, it's no solution. So folks, on problems where all of the answers end up being extraneous, your final answer is no solution. And I think we'll go ahead and stop there for today. So tomorrow we'll be continuing with solving. We'll start a little bit with graphing. Use this time to work on the homework that's due tomorrow night and also to get a start on some of the solving homework. Yep.